Welcome to this lecture series in linear algebra. In this lecture, we'll discuss the notion of cyclic degree of a vector, which is a phraseology which I coined for myself, although it is a very natural notion. And let us recall what we need. So, recall the definition of the cyclic subspace generated by a vector. Fix an endomorphism on a vector space V and a vector in the vector space. Then the cyclic subspace generated by the vector V is defined as the span of all these vectors. So you take V, then you apply T to it, then you further apply T to it, and so on. The span of this list is what is defined as the cyclic subspace generated by V. Of course, all of this is with respect to a fixed endomorphism, and hence it appears in the notation. And here is an observation that we made. So, in terms of polynomials, the cyclic subspace generated by the vector V is just apply the endomorphisms corresponding to any polynomial. Pick a polynomial, apply the corresponding endomorphism to V, collect all such things. That is a subspace and is same as the cyclic subspace generated by the vector V. So we saw all this. And here is another thing that we need to recall is that, again, we have an endomorphism T, and this time let Px be an eigen polynomial of T. Okay, and V be a non-zero generalized polyeigenvector of T corresponding to Px. So let's recall what that means. What that means is that there is some positive integer k such that this is 0. That's all that we are saying. Okay, and let k be the smallest positive integer such that this is the case. So since V is a non-zero generalized polyeigenvector, the smallest k has to be positive. It cannot be 0, because if k were equal to 0, it would mean that V is 0, but we have picked a non-zero generalized polyeigenvector. So let k be the smallest positive integer such that this happens. Then we proved, this is a theorem which I'm glossing over because all we need is this conclusion that the degree that the dimension of the cyclic subspace generated by the vector V is just k times the degree of Px. Okay, so with that, let us proceed. Here are some problems for practice. This one is marked as star because I thought that I'm going to use it, but perhaps I won't be using it. But at any rate, this is a very interesting and important problem. Also very easy. Okay. So let's define what is called the cyclic degree, or what I have called cyclic degree. I don't think this is a phraseology that you will find in textbooks. I just invented it so as to facilitate exposition. So fix an endomorphism on a vector space V and fix a vector in the vector space. Then the cyclic degree of the vector V with respect to the endomorphism T is defined as, notationally it is how we denote it, but the definition is it is just the dimension of the cyclic subspace generated by the vector V. So it's just, you might say, why even bother to give it a name? But we have given it a name. I think it's a good name. Okay, and here is a comment which might not be immediately obvious, but it will be very clear in the next slide. So what we are saying is that the cyclic degree of the vector V is at most the degree of the minimal polynomial of T. Okay, so this may not be immediately clear from what we have, from this definition itself, but just wait for the next slide and you will see that this will be very, very clear. And let us see an example. So we have an endomorphism of R5 defined by the following matrix. So this matrix is with respect to the standard basis of R5. And this is how the matrix is. So we know what the endomorphism is exactly. And let us just compute the cyclic degree of the vector E1. So we have the vector E1, and then T of E1 is, if we look at the matrix, T of E1 as 1 in the third row. So T of E1 is E3 because everywhere else we have 0. So T of E1 is E3. And now let us find T square E1. T square E1 is T of E3 because T of E1 is E3. But what is T3? So we go to the third column and we find that the only non-zero entry is on the fifth row. So T of E3 is E5. Now what is T cube E1? T cube E1 is T of E5, but that is 0 because in the fifth column everything is 0. So T E1 is E3, and then further apply T you get E5, and then further apply T you get 0. So at the very least, the cyclic degree of E1 should be 3 because in this list, if I write V in place of E1, then in this list V and then TV and then T square V, we have at least 3 linearly independent vectors, namely these 3. So the cyclic degree is at least 3. And if you give it just a little bit of thought, you will see that it is actually exactly equal to 3 because one more hit of T on E5 yields 0. So beyond the point 2, meaning after the second hit of T, every time you will see a 0, 0, 0. So this space is spanned by these 3 vectors, which are linearly independent, and hence the cyclic degree of E1 is 3. So let me just record that. But of course with respect to T. Okay, very simple example. And now let us look at the next slide and keep this in mind. Okay, maybe this is not immediately what I wanted to say. Perhaps we'll have to wait for another slide, I guess. Yeah. So let's wait for another slide to see why this is the case. Okay, so it's a very, very simple statement that we are going to say. Fix an endomorphism of a vector space V and fix a vector in the vector space V. Let D be the smallest non-negative integer such that these are linearly dependent. Okay? Then the cyclic degree of V is D. And if you follow the example that we gave about cyclic degree, this may already seem reasonable or believable. It's fairly intuitively obvious. So let's just give a proof of it without going into much explanation. So first what we have is, so let D be, so D is given, D is the smallest non-negative such that these are linearly independent. And we want to show that D is same as the cyclic degree. So first we know that this vector, this is in the span of, so why is that? These are linearly dependent. So there exist scalars alpha 0, alpha 1, up to alpha D, such that this whole thing is 0. Now, if alpha D were 0, then these would be linearly dependent, but that contradicts the minimality of D. D was the smallest non-negative integer for which these were linearly dependent. And if alpha D were 0, then we would find that the things up to D minus 1, meaning T to the power D minus 1 of V, those would be linearly dependent. And that contradicts the minimality of the integer D. So that linear dependence and the fact that alpha D is non-zero shows that this is in the span of that. So you can justify this for yourself if that was not clear. Okay, so therefore, the dimension of this is at most D. Why is that? Maybe I'll write one more line. So the previous deduction implies that if we take the span of all of these, that is same as the span up to the point d minus 1. Right? Because once this is in the span of that, every higher power, meaning you replace d by some higher number, that also is in the span of that. Okay, so justify that for yourself. So we have this is equal to that, and hence this dimension is at most t, because the dimension of this is by definition this thing, because this thing is that thing. So the dimension of the left side is equal to the dimension of the right side, but in the right side we have d vectors which span it, and hence the dimension of the right side is at most t, and we have this. So we have this inequality with us. Okay, but now let's say that the dimension of this thing be equal to k. In other words, the cyclic degree of V be equal to k. Then these k plus 1 vectors are in a k-dimensional space. Why is that? Well, they all live in the cyclic subspace generated by V, which by notation has dimension k. So these k plus 1 vectors are living in a vector space of dimension k, and hence they must be linearly dependent. So thus they are linearly dependent. And that gives that t is at most k, which is by notation. So why does it imply that d is at most k? Because that's by definition of d. D was the smallest non-negative integer for which these were linearly dependent, and k is one such non-negative integer, and hence by the minimality of the minimality of d, we have this. So d is less than equal to that, and the dimension is less than equal to d. So you combine these two inequalities, we see that d must be equal to the dimension of the cyclic subspace generated by V, hodgepodge. D must be equal to the dimension of the cyclic subspace generated by V, and this is same as the cyclic degree of V. So we have proven this very simple lemma. All right. And now here are some exercises. So the first corollary is that if T is an endomorphism, V is a vector, and D is the cyclic degree, then up to the point d minus 1, you start with the vector v and then keep applying t up to the point d minus 1. Then these d vectors form a basis of the cyclic subspace generated by v. So that's an exercise. Okay. And then again, we have the same setting. And Qx is the smallest degree monic over the base field, such that the corresponding endomorphism kills V. And there must exist such a thing because, in particular, the minimal polynomial of T is such a thing. So you collect all the polynomials which satisfy this equation, pick one which has smallest, pick one monic which has smallest possible degree, and it follows that the cyclic degree of V is same as the degree of this particular polynomial. And this will also be an exercise. At this point, we have enough maturity to argue such things. So I'll leave this as an exercise. But this is not so straightforward as the previous one. Albeit, this is also very easy. Okay, and now finally, we have an endomorphism on a vector space V, and we have an eigenpolynomial of the endomorphism. Fix a generalized polyeigenvector of T corresponding to this eigenpolynomial. And again, let K be a non-zero, the smallest non-zero integer for which this happens. Then the cyclic degree of V is K times the degree of the eigenpolynomial. Okay. And if you looked at the recall, using the recall, it is immediate that we know that the dimension of the cyclic subspace generated by V is k times the degree of the eigenpolynomial. And yeah, so we are in a sense just repeating the definition. Using the recall, this is nothing. This is a trivial statement. Even though proving this is not so simple, we had a kind of a representation theorem which is stated in blue in the recall. But anyway, we recall this particular part of it. Okay, so now let's move on. All right, so I think this will be the last observation. No, this will not be the last observation. So here we have the same setting. We have an endomorphism on a vector space V, and Px is an eigenpolynomial of it. We have a vector which is a generalized polyeigenvector of T corresponding to this eigenpolynomial. And let Fx be a polynomial over the base field, which is relatively prime to the polynomial Px. Then the cyclic degree of this guy does not change. So if you apply a polynomial, right, if you apply the endomorphism coming from a polynomial on V, the cyclic degree cannot go up. But if you choose the polynomial as relatively prime to the eigenpolynomial, of which V is a generalized polyeigenvector, then the cyclic degree is preserved. And by now these things shouldn't feel very surprising. After all, it is just Euclid's theorem that is powering all this. But we will write a proper proof. Okay, so let k be the smallest non-negative integer such that this happens. Since V is a generalized polyeigenvector corresponding to Px, such a k must exist. And as we saw in the previous slide, this means that the cyclic degree of V is k times degree of Px. Okay. So clearly, this is 0. Why is this 0? Because this is 0 and ft and pt to the k commute, if we just shuffle the positions of these two things, using this we see that this equality is indeed true. So we have that. And so assume on the contrary, the cyclic degree of this guy is strictly less than the cyclic degree of V, which is same as saying that it is at most k minus 1. Or what should I say? It is at most not k minus 1, but at most. Okay, let me write it in a different way. So let D be smallest such that this thing is 0. So that the cyclic degree of this guy is D times degree of Px, right? That's what we have just used the previous theorem once again. Okay. So assume on the contrary to the proposition that D is strictly less than K, and we want to produce a contradiction. So far we haven't even used the hypothesis that Fx is relatively prime to Px, but now we will do it. So by Euclid's theorem, there exist polynomials Ax and Bx such that this is the case, which implies so what happened? All we have done is we multiplied by this guy. Sorry, here I meant to write a k. Yeah, so we multiplied by this guy on both sides. That's all. So we have that equation, and we can therefore write that this endomorphism is equal to that thing, but we can apply v on both sides. If we do that, we can write v in all three places. But now this thing is 0. Just look at that equation. This thing is 0. And since d is at most k minus 1, this thing is also 0. I mean, this was our assumption. So this is also 0. And therefore, the right side is also 0. But if the right side is 0, we are contradicting the minimality of k. And that gives a contradiction. I'm not writing all that, but that gives a contradiction. So this was 0, that was 0. And therefore, the right side is 0, but the right side is 0 gives a contradiction to the very assumption on the non-negative integer k. And now here, the very careful reader will notice that here k was assumed to be greater than or equal to 0. So this might not make sense if k is 0. But if k is 0, then you can finish the proof separately. So in the entire proof, we can assume that k is at least 1. So that writing this is meaningful here, because raising px to a negative power is meaningless. Alright, so all those boundary cases I'm not concerning myself with. And now for the last proposition. So again, we have some endomorphism and an eigenpolynomial of it, and a generalized polyeigenvector corresponding to that polynomial. And let us say the cyclic degree of v is m times the degree of this eigenpolynomial, which again means that the smallest non-negative integer for which k for which this thing happens, I mean pt of k applied on v gives 0, is m. That's what this means. I mean this was a theorem. And okay, so we have cyclic degree is equal to m times degree of px. And let fx be such that the corresponding endomorphism kills v. Then px to the m divides fx. So that's a very nice thing. And let's just immediately or quickly prove it. So say k be largest. I mean, what we are doing is fx may have some, px as a factor or some highest power of px as a factor. So first we will write fx as px to the power something times something that is relatively prime to px. So what I'm trying to say is that let k be largest such that this time gx, where, I mean, it just follows that. And yeah, so even before I proceed, so why should, I mean, what does this even, why are we writing this? All we are saying is something like this. Suppose you have the number, let's say 18. 18 you can write as 3 squared times 2. 3 is a prime, and you can extract the highest power of 3 and write the remaining stuff. That remaining stuff will be relatively prime to 3, right? And this is the polynomial analog of it. Px is an irreducible polynomial. Because it is an eigenpolynomial, it is an irreducible polynomial. So it is in analogy with primes when you talk about integers. So this guy will be relatively prime to px. And yeah, so that's all that we are doing. So we have px and gx are relatively prime. Okay. Okay, so now by hypothesis, we have 0 is equal to ftv, which is by our notations equal to that. Or maybe I will write it this way, because the things commute, so it doesn't make any difference. You can write it that way. Okay. But the cyclic degree of this thing is same as the cyclic degree of this thing. Why is that? Because gx is relatively prime to the eigenpolynomial px. Therefore, by the previous proposition, the cyclic degree of this vector is same as the cyclic degree of this vector. This is exactly what the previous proposition was. Okay? But this guy is 0. Just look at that equation. So this guy is 0. And hence the cyclic degree here is 0, which implies this better be 0. Right? If the cyclic degree of some vector is 0, that vector better be 0. So we have that. But then this implies that k is at least m. Because when we had said that cyclic degree of v is m times the degree of px, by what we have proven earlier, m is the smallest non-negative integer for which this thing is 0. And we have pt to the kv is 0, so k has to be at least this smallest non-negative integer. Okay, so k is at least m, and therefore px to the m divides fx. That's exactly what we wanted to show. So maybe here I should have written the line that want to show that k is at least m. So this is what we were going for. Okay, so some corollary. I mean, I don't know if we will exploit this in upcoming lectures, but at any rate, it helps us familiarize ourselves with the concept of cyclic degree. Okay, so in the next lecture, we'll prove some very interesting things about cyclic degree. And with that, I want to end this lecture. And as usual, like, comment, share, subscribe. And I'll see you next time.